Hey guys, welcome back. In this session, we are going to take a look at some examples of recurrences. This will give us an idea of what different forms a recurrence can take. So, in our previous lecture, we looked at an example where we were searching an array and trying to find a number in that array. And what we were doing is we were reducing the array size by 1 in every recursive call. And then we were checking if the value at the end of the array matches the value we want to find. So if we look at that example at a very high level, it was something like that. A function which was taking an array of size 1 to n and a number to find. Okay, and inside this, if value at n is equal to find, we are done. Otherwise, we will call this function again with the value 1, 2, n minus 1 and to find, right? So then this line takes this, and this line of code is right, and the total is okay. So this is an example where the recurrence is reducing the problem size by 1 and trying to solve a problem. Let's take another example. In this example, we are going to look at merge sort. So how merge sort works? We have, let's say, an array, and we want to sort this array. Let's see, 3, 4, 2, 1. Okay. What we do is we divide the array in half and call the same function on the left side and on the right side. Okay. And then we again on the left side of array divides it into half, calls the same function for the left side and call the function on the right side. Same for the right half of the array. We again call on the left side and call on the right side. So if you see, we are dividing the array by 2, and then we are making 2 calls, one for the left side and one for the right side. So if we see here, this is our first call where the problem size is n. Here we divided it by 2. Okay. So this is a recursive call. Okay. Now again, we divided it by 2. So if here n is equal to 4, then here n is equal to 2. Okay, which means the array size becomes 2 and the array size becomes 2. Now here we are again dividing by 2, so our n becomes 1, right? So this is, if we see, what we are doing again is every time we are calling the merge sort function twice. Okay, so this means until here, every time we are doing which is 2. Okay, after that, this part is the divide step. For those who don't know how a merge sort work, I would recommend have a look at the merge sort algorithm so that you have a better understanding of what's going on here. After the divide step, we do the merge step, and that is why merge sort is a divide and conquer paradigm. So we are going to merge these two and sort them. So this is already sorted. 3, 4. We do the same again and merge them and sort. We do it again, merge them and sort them. So this array is already sorted, this array is already sorted. We just need to merge both the arrays in sorted form. So it will be 1, 2, 3, 4. Okay, so if you see, in every merge step or the conquer step, how much work we are doing? N times. Okay, if we look at the code, let's say the function is merge sort and we pass an array 1 to n. Okay, and then a left side and the right side. What we do is we take out middle of this array and then we call this function again for array 1 to mid on the, which means our left will be 1 and right is equal to mid. And then we call the function again for mid plus 1 to right. And so left is equal to mid plus 1 and right is equal to r. Okay. So these two recursive calls are dividing the array by 2. And if we add them, this turns out to be okay. After that, we have the merge step. What merge steps do is it sends this array 1 to n and merges it. So this is doing n work, right? Because it is sorting the array from 1 to n. And so this whole thing takes okay. So that's how we came to this recurrence. So then merge sort recurrence looks like two t plus n if n is greater than n. But if n is equal to 1, then how much work we are doing? We are just doing one work or a constant work. So this is the merge sort recurrence. Okay. Let's take another example. Example 3. Binary search. Okay. What happens in a binary search? We search a value in an already sorted array. So this is an array and it's already sorted. What we do is we take out the midpoint and we check if the number to be found is less than the value at mid or greater than the value at mid. If it's less, we go on to the left side. So let's say we go on to the left side. What we did, we divided the array in half and called the function again. Now we again look at the mid and check if the value to be found is less than the value at mid or greater than the value at mid, right? If it's equal to value of mid, we have found the value and we end our search. So let's say it's greater than the value at mid, right? So this keeps on going until we find a value. So at every step, we are dividing the array by 2, right? So what will be the recurrence look like? That's it. So here we see that we are dividing, but a binary search does not have a conquer step. There is nothing. It's only divide. Okay. So how the code looks like? Let's say binary search takes an array 1 to n. Okay. And inside, what we are doing, we check if value is greater than value at mid. So then what we do, we call the same function on the right side of array, which is mid plus 1 to n. Else we call on the left side, which is 1 to mid, right? Something like that. So this is an example of binary search recurrence. So we have taken 3 examples of different kind. One where we are not dividing the problem size by fraction, but instead we are reducing the problem size by just 1. Here in merge sort, we are dividing the problem size by 2. And then there is a constant work which is taken on time. Then there is a third example of binary search where again we are reducing the problem size by half. Okay. So these are some of the examples which a recurrence can take. Let's take a random example. Which might make sense in the form of recurrence, but probably this code won't be used anywhere, or maybe. Let's see. So let's say our recurrence looks like if n is equal to 1 or t 2n upon 3 plus t n upon 3 plus on. Okay. This is another example of a recurrence. Now, if we see how the code will look like, let's say we are getting a problem of size n. So what might we be doing in our code? Let's say we are calling the function recursively again, and we are dividing the problem by 3 and multiplying by 2. Then for this call, n upon 3. And then for this, because it's doing n work, this means we might be running a for loop from 1 to n and doing some work here. So then this is and this is not recursive call. This is just running n times. Make sense? And this turns out to be this recursive recurrence relation. There might be more examples. It could be like this. If n is equal to 1, or right? So I would say try to do a pseudocode for this, how the code might look like for this recurrence relation before you go ahead. So maybe pause the video here, try it and see if your solution matches mine, so that you know that if you are getting a good understanding of recurrences. So I will move ahead, and so now you see we are dividing the problem size by 4 and doing it 3 times. So then maybe in the code it's something like n upon 4, n upon 4, n upon 4. So then this is Tn upon 4, this is Tn upon 4, this is Tn upon 4. And this total will be 3T. What else? We have a work being done which has a asymptotic complexity of n square, which means we might be running 2 for loops, right? So maybe the code is for 1 to n, for 1 to n, and some work. So then this is O(n) square, and we add this, comes out to be this recurrence, right? So these are just some random examples where you have a recurrence and how the equivalent code will look like. I hope this session might given you some help and insight into recurrence relations and how they are created out of code. So I'm going to end this session here, and I am going to see you in our next session on recurrences, where we will dive into how to solve these recurrences using different methods. Bye for now, and thanks for watching.